Hello everyone, I hope you're doing well. In this video, we'll see how to find out the linear density for FCC directions, and these are the three directions whose linear density we'll be finding out: 100, 110, and 111. Previously, I have done the similar video, which is to find out the linear density for FCC direction for these three directions, but the language of instruction was Urdu and Hindi. But I was noticing that there were many viewers who are from United States and other countries, and I know their preferred language is English. So that is why for those viewers I'm doing this video. So if you are preferring Urdu and Hindi as language of instruction, then that video link will be in description box. So let's start with the video now. First of all, we'll mention the formula for linear density, which is let us denote it with lambda sign. Okay, I'm denoting it with lambda sign. You can denote it with other signs, other preferred signs as given in your book, because in different books the notation is different. That lambda or linear density, linear, it's linear. So linear density equals net number of atoms lying on the line divided by the total length of the line within one unit cell. Okay, one unit cell will be considered, and the net number of atoms that lie on the line divided by the total length of the line. Let us denote the net number of atoms lying on the line with capital N and the length of the line by capital L. Okay, so lambda equals capital N by L. This is the formula that we'll be following in order to find out the linear density for FCC or any other crystal system. Now, the first direction in Q is 100 direction. This is the simplest one, and the first step is to draw the unit cell. Okay, we'll first draw the unit cell, then we'll draw the direction, and after drawing the direction we'll see what is capital N for this direction, and then we'll find out the value of capital L. And here we are. These are the three coordinate axis directions, and since the Miller indices 100 are positive, that is why the preferred origin for me is this one. Okay, for positive Miller indices, the origin is this. This is, let's say, x-axis, this is y-axis, and this is z-axis. Okay, and since it is a cube, so all these lengths from one edge to another edge along the axis direction will be equal, and let's say these lengths are a, small a. Okay, this length be small a and this length is small a, since it is a cube. So all these lengths which are parallel to the axis lines are equal in length, and they are a. Okay, so next step is to draw the direction, and in drawing the direction you always take the LCM of the digits, non-zero digits right there, which is 1 here, and divide them with all of the Miller indices, like non-zero digits. 0 is not considered. Okay, the 1 is digit right here, which is non-zero, so LCM of 1 is 1 again, so we'll divide 1 with all of these value and we get 100 again. Okay, this is the first basic step that you need to perform in order to draw the direction from Miller indices. This is the basic step, and that is why I mentioned here, because if you are given this direction like 210, okay, so the first step to draw this direction is to divide the LCM of non-zero values here. So the values are 2 and 1 as non-zero digits, so taking the LCM will be 2. We'll divide the 2 with all these three Miller indices, 2 divided by 2, 1 divided by 2, 0 divided by 2, and we get 1, 1 by 2, 0. So these are the coordinates, final coordinates, which we will be using to draw the direction. Okay, so this is the basic step, and it is not necessary when these are the Miller indices, but I just needed to mention it just in case your tutor gave you some these kinds of directions and told you to find out the linear density for these directions. So the first step will be to divide the Miller indices with the LCM of the non-zero indices. Okay, so non-zero indices will be taken out as I mentioned right there. So 100. Now after dividing with the LCM, these are the coordinates corresponding to x. First is for x, second is for y, and third is for z. Okay, these are the coordinates, and coordinates are used to draw the directions or position vectors. So from origin, first of all, you need to move 1 unit along x-axis. 1 unit along x-axis means from one corner to another corner along x-axis. This is x-axis, so we'll move from this end to this end. Okay, like that. This means 1 unit. Moving from from origin to this half point will be half. Okay, half units, and complete unit means to the other end of the unit cell. After moving to the other end of the unit cell, the y coordinate is 0 and the z coordinate is 0 also. It means you do not need to move any further along along y and z axis. Okay, so this is the final destination and this is the initial point. So the vector will be from initial to final like that, and this is the vector 1 0 0. Okay, now since the crystal system is FCC, so we know that where the atoms are possibly lying on this line. So this is the one of the atom and this is the other atom. Okay, all other atom will lie outside of this line. Okay, all other atom will lie outside of this line. One is there, one is there, and all other atom will lie outside of this line. So drawing them will be extra detail that doesn't needs to be there. Only these two atoms will be there and some of their part will be contributing to the line. So now what part of the atom is contributing to the line is determined from the fact that if the line is intersecting the whole diameter, of the is touching the whole diameter or intersecting or passing through the whole diameter of the atom, then we consider its contribution to the line as 1. If the whole diameter is being cut by the line, if only half of the diameter is being cut by the line, then we consider as its contribution to the line to be 1/2. Okay, it is determined from whether the line is intersecting the whole diameter. If it is whole diameter, then 1 contribution is taken, and if it is only half diameter, which is radius, from center to the edge of the atom is radius, or we can say it is half the diameter, so its contribution to the line will be half. Okay, now in drawing the atoms, the center of point of the atom lies on the corner of the unit cell. So this is the corner point, and from corner to the edge of the atom is radius, and radius is half the diameter. So only half the atom, you can see here that this line is not extended in backward as like that. Okay, it is starting from the center point of the atom. It is starting from the center point of the atom and it is moving in this direction to the edge of the atom. So this is half the diameter, so only half of this atom is within the line within a 1 unit cell. Okay, so only half contribution of this atom is there, and for this atom the similar case is there because the center point of the atom, since we are considering the atom to be spherical, so the center point is there, and from center to the edge is within this line. So from center to the edge is half diameter means half contribution to the line. This half is not there in within that line. Okay, within a single unit cell. So half by this atom and half by this atom. So the total number of atoms that lie on the line is 1/2 by this atom and 1/2 by this atom. We will add these contributions and we get 1. 1/2 plus 1/2 is 1. So net number of atoms that lie on this line are 1. Now next is to find out the length of the line, and this is the line, and we can see here that this length is already we already know that it is a length. Okay, which is lattice parameter. So from one edge to another edge along the axis direction, along the since it is along x-axis, from one corner to another corner is lattice parameter, which is a. So the length of the line is a here. Okay, so the linear density for 1 0 0 direction will come out to be 1 divided by a. Now if you were required to find out the linear density in terms of the lattice parameter, then you are like done. But if you are required to find out the linear density in terms of the atomic radius of the atom forming up the FCC lattice, then an additional step is needed. For FCC crystal system, there is a fixed relationship between the lattice parameter a and the atomic radius capital R. Atomic radius means the this atom is spherical in shape and it has a particular radius capital R. Okay, you can express this length a in terms of the capital R radius of the atom. Okay, and for FCC lattice it is 2/2 capital R. A equals 2/2 capital R. We can also derive it very easily from the fact that these atoms that are on the phases, these diagonal atoms are completely connected with each other, and if you draw a vector from this point, center point of the atom, to this center point of the atom, then here is the vector. This length is a, this length is a. Okay, and this length can be estimated in terms of the radius of the atoms, because this is from this point to this point, from this point to this point is one atom's radius. Okay, and this distance is the whole diameter of the atom, which is 2r, which is equals to 2r, and this is again r. Okay, this distance from center point of the atom to the edge of the atom is capital R. From one edge to the other edge of the atom is 2r, which is diameter, and from center to the edge of the atom is again r. So if you add these distances up, you will get the distance length of this line in terms of the radius of the atom. Okay, so the length of the line will come out to be r plus 2r plus r, which is 4r. Okay, so the length of this line in terms of the radius is 4r. This length is a and this length is a again. So we'll use the Pythagoras theorem since it is a right angle triangle, and this two lengths are perpendicular to each other. Okay, this is base, this is perpendicular, and this is hypotenuse. So we'll use it. Hypotenuse is 4r, its square equals a square, which is perpendicular, and a square, which is base. 2a square, which is 16 capital R square, and if you divide 2 right there, we'll get 2, and this is 8. 8r square equals a square. Taking under root on both sides will give 8 under root r. Under root 8 is 2 under root 2 r. Okay, you can easily find under root 8 as 4 multiplied 2. We can distribute the under root on both multiples. Okay, under root of 4 is 2, so 2 under root 2. Okay, so a equals 2 under root 2 capital R is a relationship between lattice parameter a and atomic radius capital R for FCC lattice. Okay, it is true for FCC lattice. Only for BCC lattice it is something like 4 divided by under root 3 capital R. Okay, this is for BCC lattice, but for FCC lattice this is the relation. So we'll put the value of a right there, which is 2 under root 2 capital R, and this is the linear density in terms of the radius of the atom. Okay, and if you are given the radius of the atom, let's say the atom is, let's say, cesium atom, and its radius is, let's say, 1.6 angstrom, you will put the value 1.6 angstrom is 1 angstrom is 10 is 10 meter. So you'll put this value of radius. If it is if radius is given, then you will put the value of radius in this expression. If the lattice parameter is given, then you will put the lattice parameter in this formula. Okay, it depends upon which value is given. You will use the formula accordingly. So we'll plug this value into this formula, and you'll solve it using the calculator. The numerical value will be there, and the units will be atoms per meter. Okay, the units will be atoms per meter. So we have completely successfully found the linear density for 100 direction. The next one is 110 direction. So the first step is to draw the unit cell, and I'm drawing it now. Okay, so these lines should be straight, and in paper you need to draw it in with ruler. Okay, so that your cube looks perfect. This is the origin, this is x-axis, this is y-axis, and this is z-axis. All right, so for this is origin. Now we'll draw the direction 110, and for this we need to first divide the LCM of non-zero digits right there, and LCM is 1, and dividing with 1 will bring no change in them, so we'll use them as coordinate. This is x coordinate, this is y coordinate, and this is z coordinate. Okay, so x coordinate is 1, y coordinate is 1, and z coordinate is 0. From origin we'll move 1 unit along x-axis. 1 unit means to the other corner of the unit cell along the x-axis. Okay, this is 1 unit along x-axis, then 1 unit along y-axis, and this is y direction, and we'll move from this to onwards along along the y direction, and this is the y direction, and along z direction there is no motion at all, as represented by the 0 digit. So there is no motion along z-axis as the coordinate is 0. So this is the final destination, this is the initial one. So a vector will be drawn from the initial point to the final destination, and this is the vector, and this is the 110 direction also. Okay, this is the desired vector. Now we'll draw the atoms that possibly lie on this line, and these atoms are, we know that this is FCC lattice, and there is a atom right there, and there is an atom in the face of the unit cell, which is this. Okay, and another atom at the corner, like that, and these 3 atoms in the diagonal are completely attached with each other. There is no distance in between. Okay, there is no gap in between. They are completely attached with each other. Okay, none of the other atom will lie on this line since it is a 2D line. So the formula is lambda equals capital N by L. Okay, the total number of atoms that lie on this line could be found at the similar way as I told earlier. For this atom from center to the other boundary point, only the half the diameter is lying on this lines. Okay, so half contribution by this atom and half contribution by this atom also. Okay, for the similar reason as I told earlier, but this atom's whole diameter is being intersected by the line. Okay, that is why the whole atoms is there, that is 1 is taken as the contribution by this atom. Okay, because the whole diameter is within the line, only half diameter is there, and half diameter is there for these 2 atoms. So half plus half for these two atoms and plus 1 for this one atom. And lastly, we need to find out the length of the line. This is the length this is the line whose length we need to find out, which is, let's say, capital L. This length is A, as we know. This length is A also. Okay, these lines are parallel to the axis, that is, this line is parallel to x-axis, this line is parallel to y-axis. So from one corner to other corner along the axis direction, the length will be A. Okay, but this line is not parallel to either x-axis or y-axis or z-axis too. So we need to find out its length, and using the Pythagoras theorem, L square equals, this is base, which is A square, plus perpendicular, which is A square. So L square equals 2A square. L will be equals to, taking under root on both sides, under root 2A. Okay, so the length of the line is under root 2A. All right, and we need to find solve it. 1 by 2 plus 1 by 2 is 1. 1 plus 1 is 2. 2 by under root 2A. Okay, and 2 by 2 under root 2A can be further solved as follows, as 2 to the power 1 is 2, 2 to the power 1 by 2 is under root 2. So bases are same, so power could be added 1. Since this one power is in the denominator, it will come with negative sign above, divided by A, and it will come out to be 1 minus 1 by 2 is 1 by 2. So we are left with under root 2 by A as the linear density for FCC lattice in 110 direction in terms of lattice parameter. And we know that A is equals to 2 under root 2 capital R, the atomic radius. So the linear density would come out to be, after inserting the value of A, 1 over 2 capital R. So this is the final result for the linear density in 110 direction in terms of the atomic radius. Okay, so lastly we will be finding the linear density for 111 direction, and let me know if you want me to find the linear density for other directions also. Normally other directions are not given in paper by teachers. These 3 directions were given, but just in case you want me to do this, so first of all we'll draw the unit cell. Okay, and here we go. You just need to understand the positions of atom for FCC and BCC crystal systems, and after that you are like good to go if you know where the atoms are, and if you know these diameter thing, then you are sorted. Mostly it is either 1 by 2 or 1. Okay, so this is the origin, okay, for positive Miller indices, and 1 is again the LCM. If you divide 1 by each of these value, you will get again 1 1 1. So this is the coordinate for x, this is coordinate for y, and this is the coordinate for z. Okay, so these are the coordinates. From origin we'll move 1 unit along x-axis, okay, 1 unit, because it is 1, along y-axis, okay, and 1 unit along z-axis. So from this to this. So this is the final destination that we got after following these coordinates. This is the initial point and this is the final point. We'll join these 2 points to get the vector, and this is the line vector for 111 direction. Okay, this is the line vector for 111 direction. All right, now we need to find out the linear density, and the linear density is equals to n divided by L. Okay, for n we know that one of the atom obviously lies there and the other atom lies there, and since it is a FCC, face centered cubic, there is no atom in the body center. Okay, this is from one corner to the other corner, and these are the 2 opposite faces. One face is there and the other face is there, and you are drawing a vector from this point to that above point. Okay, so there is no atom in this centermost point, body center point in FCC lattice. So these are the only 2 atoms there, and again half contribution by this atom and half contribution by this atom. Okay, so for n we have 1 by 2 plus 1 by 2. None of the other atom is lying on this line, and for the length we can find its length by using the Pythagoras theorem, and let us draw the right angle triangle, this line here and this line. This length is under root 2a, as we already know. This length is a, we already know, and this length needs to be calculated, which is capital L here. So using the Pythagoras theorem, L square, which is hypotenuse here, this is the base, under root 2 a square plus this one length, which is a to the square, and we'll get 2a square plus a square, which is 3a square. Taking under root on both sides, we'll get under root 3a. So the length of this line is under root 3a. Putting the value right there, we got 1 by 2 plus 1 by 2 is 1. 1 by under root 3a. This is lambda. Okay, this is the linear density in terms of the lattice parameter A. And if you want to express in terms of the atomic radius, so we can also do it by putting the value of A right there, and we'll get 1 over under root 3 into 2 under root 2 A. Oh, sorry, capital R. And joining the two under roots together by multiplication sign, we get 1 over 2 under root 6 r lambda. This is the value of linear density for 1 direction in terms of the atomic radius capital R, and the units are similarly atoms per meter. Okay, if you solve the prefix also, so this is it. Okay, I have also done it for BCC lattice in English as language of instruction, so you can check out that one video also. The link will be in description box, and I hope you got what you needed. And like, share and subscribe, share it, and share it with your fellows. It will definitely help them and also me. Thank you so much. Goodbye.